Okay, good. So we have, Austin, I'm gonna ask you to monitor the chat while I go through this stuff. So interrupt me at any point as I go. All right,
Sounds
so
good.
we're moving now to talk about path analysis, and I'm hopeful that we'll get through both path analysis and confirmatory factor analysis, but we'll see how far we get. So I'm going to start with an example. This is a study that was done in 2009 by Anton, and they were examining the role of stress, this is really funny, in workers' behavior, and looking specifically through job satisfaction and organizational commitment, which they talked about as a commitment to the well-being of their workers. And so they did a nice complicated analysis, and here's kind of their theory. The first thing they talked about is that people in their jobs might end up with something called role conflict. And role conflict, let's take a GA as a job, a graduate assistant or a teaching assistant. Role conflict might be, for example, if you're a GA, that your mentor says to you, I need you to do this thing for the lab. I need you to work this amount of time and fix these things in the lab. But at the same time, because you're a student, you're also being asked to do things like devote time to your studies or to making progress on your milestones. And you only have a certain amount of time in your day, but you have to figure out what's the best way to do all the things you have to do to be a good student. So you have to be a good lab manager, you have to be a good making progress on your milestones, you have to be keeping up with your classes. All that can create role conflict. And if you have role conflict, then these people hypothesize that there would be greater role ambiguity. Like, where should I be putting my time? What's really going to matter? What is my job exactly? If you have role conflict and role ambiguity, they hypothesize that this would lower your job satisfaction, or in this case, maybe grad school satisfaction. Furthermore, if you had role conflict, you were going to have lower what's called affective commitment. So maybe you weren't going to feel like so connected to the University of Arkansas. Maybe you weren't really going to feel like a good Hog fan or not be proud of where you were. And the more role ambiguity you would have, the less affective commitment you would have to the university. In contrast, the higher your job satisfaction, the more maybe affective commitment you would have to the university. So here, wherever we're hypothesizing a negative relation, such as one goes up, the other goes down, I'm indicating that with red arrows. And positive commitment, I'm indicating that with green arrows. Notice also that the arrows are one way, that they originate in one variable and they lead to another variable. So we're actually thinking that, for example, higher role conflict leads to lower affective commitment, and not that affective commitment leads to lower role conflict. Okay. Then they said that if you have low affective commitment, basically you're like, I don't give a shit about University of Arkansas, then you're going to have greater turnover intentions, meaning the desire to leave. You're going to do worse in your job performance, and you're going to have higher absenteeism. Or said another way, if you feel good about where you are, you have high affective commitment, then there'll be lower, say, dropout or turnover, higher job performance, and lower absenteeism. And they further said that role conflict will directly lead to turnover in tension and lower job performance, and that job satisfaction will directly result in lower turnover in tension, and that role ambiguity would result in higher turnover in tension and lower job performance. So they had a lot going on here in their study. So the general purpose and description of path analysis, we're really talking about simultaneous multiple regression. And as we'll see in our lab, we're going to break it down so that it's pretty clear that really this could all be answered by just doing a set of regressions. In the case, say here to here, There's this one arrow here. And that could be answered by just putting a thing where you're predicting role ambiguity is being predicted by some intercept plus some weight times role conflict. Okay, that's just one of the regressions. We also have, for example, turnover intention. This could be our next Y. This is being predicted by role conflict, this X. It's also being predicted by affective commitment, and it's being predicted by role ambiguity. So this Y2 is being predicted by X1 role conflict plus X2 role ambiguity plus X3 affective commitment. So you can really break down every one of these relations into a set of regression equations, linear regression equations. And that's why the best way to think about path analysis is that it is just simultaneous multiple regression. You're simultaneously solving all of these regression equations. Path analysis is part of a larger collection of confirmatory statistical techniques that all fall under the umbrella of structural equation modeling. And we make special use of drawings, which we call path diagrams. And we're going to talk a lot about these conventions for how to draw them and what they mean, because they convey a lot of important information. The minimum data set that you need in order to run a path analysis is one IV. Of course, we can use more. Also, they can be any kind of IV. So you can have continuous IVs, dichotomous IVs, or a mix of continuous and dichotomous all in your model. In structural equation modeling, we call these exogenous variables. And it's exo because that means outside of. Exo means that how they came to have their value, how did the X happen to be whatever score it was, is not of interest to us. We don't give a shit about how it happened to be that you were born male or female, or how you happen to have role conflict. That's not of interest to us. What we care about is that you have that. That's a starting point, okay? And the other thing that we need for our data set is one or more DVs, which also can be continuous or dichotomous or a mix of DVs. And we call those endogenous variables. Endo meaning that the reason they came to have their value is explained from other variables in the model. So the explanation for their value is in the model. That's why we call them endogenous variables. Any questions so far? Since I can't see the chat or anything, Austin, I'm needing you to help me.
Nope. It looks like we're all good.
Okay, excellent. Okay, so let's talk a little bit about what's happening behind the scenes. Structural equation modeling, which I'll call SEM generally, and path analysis particularly, start with your known covariance matrix, which is just your unstandardized correlation matrix, right? The correlation matrix, but in its original metric. So they start with the covariance matrix. Then, just like we saw in EFA and PCA, they try to reproduce that covariance matrix with a model that you specify. So when you do your equations or you draw your diagrams, you're basically telling the computer, or in this case R, the reason somebody has a turnover intention is because they have role ambiguity or role conflict or affective commitment. You're saying it's not because of, say, job satisfaction. So you're telling the computer basically already there's going to be overlap and variance between these X variables and this other Y variable. And also there's not going to be overlap, or there's going to be functionally a correlation of 0 between these X variables and this Y variable. And then the program will basically take your model and try to fit the data to the parameters you have set. So you force certain things to be related to each other, and you forced other things to be unrelated to each other. and it tells you how well did it reproduce the covariance matrix with the real data. And then the way we can tell how well it did so is through these various fit indices, a chi-square test of significance, how many iterations it took for the model to reach convergence, and the analysis of residuals or error and unexplained variance. And we're going to practice all of these things. So let's talk about the simplest kind of path analysis. I probably could have made this even simpler by just using one variable predicting one other variable. Structural equation modeling is the kind of like, again, larger family, and it is a combination of exploratory factor analysis and multiple regression. But in its simplest form, the one that is the focus of this part of the class, structural equation modeling is multiple regression, or really in its absolute simplest form, it's just correlation. So these are variables that all come from our data set. These should be familiar to you. We've got these middle school kids, they reported on their parental education, we have their math and reading scores, and we have their GPA, let's just say at time 1, just because the other variables were all collected at time 1. And we're using all of these to predict education 3, okay? If I were to give you this picture and ask you to write the regression equation that corresponds with this picture, what would that regression equation look like? We're going to talk in a moment about sample size and all that. Okay. So all regression equations look like is y is some intercept plus some b weight plus some x variable plus some b weight plus some other x variable, and so on and so forth. And so Casey threw in there that we would have basically education 3 is predicted by some intercept plus some b weight times father ed, plus some other b weight times mother ed, plus some other b weight times SMA, and so forth, right? All the way up through b weight times GPA 1. So you guys already know how to do path analysis. You've just never done it in this way before. You've always done it by just writing out your equation and doing this one analysis. So we can run the same thing by drawing a path diagram, and there are some additional things we're adding here. The first thing is when you run a path diagram, you are by default, actually, SPSS is going to do, I'm sorry, not SPSS, R is going to do a few things for you. There are these arrows over here. We haven't seen those before, okay? In the example that I drew here, the arrows are only connecting mother ed and father ed. They're only connecting SMA, GPA, and SRA to each other. But what R is going to do behind the scene is it's going to connect every one of these to every one of the other ones. And it's connecting them through the use of two-way arrows. A two-way arrow like this just indicates a covariance or correlation. These are all what kind of variables? The ones that are all on the left side, according to the definition I just gave you.
They are exogenous.
Exactly, yes. They're exogenous because how they came to have their value has nothing to do with what's in the model. They just, people's father education differed. We don't know why. One of the way that you know exogenous variables are exogenous is there are no one-way arrows pointing to them, okay? There might be two-way arrows pointing to them, such as this covariance arrow, but there's no one-way straight arrows pointing to them. So if you ever see a path diagram where there is a variable with a one-way arrow pointing to it, including, by the way, this arrow, that's how you know that it is an endogenous variable. So what I showed you here was just the covariance between mother ed and father ed. We don't know why they have their values, but we do know that they might be related to each other. So we draw that arrow. And like I said, R automatically draws the covariances among absolutely every one of these variables. And it just does that because it's like, I don't give a shit why you have that value, but it might be related to these other exogenous variables. So someone asked if endogenous variables can have covariance arrows, and the answer is no. Endogenous variables can only have one-way arrows pointing to them. So exogenous variables never have one-way arrows pointing to them, and endogenous variables can never have two-way arrows pointing to them. The other thing that you're going to see besides these covariances on the left-hand side of the model for the exogenous variables is that every endogenous variable with one-way arrows pointing to it will automatically end up with this residual variable, okay? Which again, it just means error. And so what it's basically saying is, if I predict education 3 scores from these X variables, I'm not going to predict them perfectly. There will be some errors that I make. And so to model the errors that I make, I have to include this residual term, which means education 3 is a prediction of both all these X variables plus error. And in fact, when you first drew linear regression equations outside of R, you should have learned that the prediction of Y is our good old linear regression equation plus, it actually isn't the prediction of Y, it's just Y, plus an error term. Did you guys learn all about that? Good. So the error term that is part of the real Y scores is being modeled here in this residual in our path diagram. Okay, so a few things I want to note. The first is that every endogenous variable has to have a residual term. And because every endogenous variable must have a residual term, we often don't even draw them on our when we're, say, publishing. It's just known that it has a residual term. You have to know that if it's endogenous, there's an arrow pointing from the error term to that endogenous variable. But because every endogenous variable has one, typically by convention, we don't draw them. It's just extra. So, but you should know that it's there. The covariances among the exogenous variables, on the other hand, even though R defaults to having all of the exogenous variables correlated with each other, not everybody draws them that way. And so a lot of times you will see the covariances among the exogenous variables drawn in a model. If you don't see them drawn in the model, then you should read carefully to make sure that the analysis or the article specifies that all exogenous variables were allowed to covary. Okay, so questions so far? Okay, moving on. When I actually ran that model, by the way, this is the output that I got. This represents the standardized covariance between mother ed and father ed. Standardized covariance is the same as a correlation. This represents the covariance between SMA and SRA. This represents the covariance between SRA and GPA. And this represents the covariance between SMA and GPA. Somebody asked if it's a problematic not allowing them to covary. It's not problematic from like a sketchy practice perspective at all. what it is it's more likely to result in a shittier model fit. Because, for example, let's say that it's true that the parental education is actually associated with people's achievement, which wouldn't be crazy to hypothesize. If my model doesn't specify those covariances, then I might be actually fitting a worse model. The model might fit worse because it's like, wait a minute, these are associated with each other, but you forced it to be 0, and now my reproduced correlation is shittier because my reproduced correlation matrix is shittier because of it. So typically it just worsens model fit if you don't model all the covariances. But it's not really sketchy from like a p-hacky type perspective. It's actually the opposite. Okay, so we've got all our covariances. Again, we typically don't interpret them because we're not really concerned with how people came to have the values of scores they have on their exogenous variables. Here is our endogenous variable. Up here, and this won't necessarily be the case with our output in R, but it's important to see, this represents R squared. So as a whole, the set of achievement variables predicted 32% of the variance in education 3, which also means that 68% of the variance is unexplained. And that's captured in here. In fact, this path would be 0.68. Okay. These represent the equivalent of your betas. Okay, at this point, we're looking at it as a standardized path diagram. So based on these betas, which is the strongest predictor of education 3? Good, everyone's throwing in GPA, that's right. And we didn't look specifically at all the details, like, you know, the p-value and the Wald and some other things like that, but, or the T, I mean, or Z. But yes, this one, at least on the surface, certainly appears to be the strongest predictor of education 3 because it's got the largest standardized beta. Okay. So if this is comfortable to you, then you've already got the basics of path diagrams and path analysis down. We're just going to start building off of this base and start to make it more complicated. First thing I want to know is this comfortable to you? Good. So Josh is like saying he loves the arrows and numbers. I do too. I love drawing analyses. I think it's so much more intuitive than the way that, than drawing equations, but we have to understand that if you look at a picture, you should be able to then draw the equation, but that's how we think, right? We think in terms of like how things connect to each other. This leads to that, and then that leads to that in turn, and so forth. So the path diagrams are really, really nice. And of course, we just want to make sure that we remember that everything that is endogenous has that error term that has to go to it. Okay, so let's build on this a little bit and talk about some conventions. There really are rules for how to draw your pictures. And when you start doing your own article critiques or your own write-ups and your own analyses using path analysis and SEM, it's very important that you understand these rules and adhere to them because they convey important information. The first thing is that typically we have 2 shapes that you see in a path diagram, a square or a rectangle, so some kind of parallelogram, and a circle or an oval. If a variable is represented with a square or a rectangle, that indicates that it is a measured variable. Measured variable we also call manifest variable. And what that means is that that is an X, that is an X variable that exists in our data set as an X variable, such as education 3. Okay. We actually got that from a direct measurement of some kind, or we got that through the generation of a subscale score or a total score, such as when we did DEP 1, which was the average of DEP 101 through 104. But the point is that if it's a square or rectangle and you were to pull up the data frame, you would be able to find it in a column somewhere. Okay, that's what we call manifest. Circles or ovals represent what we call latent variables. So if it's manifest, it means it's overt, it's visible, it's directly visible. And if it's latent, it means it's like underlying, right, or not directly visible. A latent variable is basically like a factor, just like what we just did with a PCA or EFA. It's a factor, meaning if I were to look in my variable, like in my data set, data frame, we just went from X1 all the way to X16, and from there we extracted 4 factors, right? We had a discrim factor, a depression factor, positive self-esteem, and negative self-worth factors. But if you look at your data frame, you're never going to find in the data frame negative self-worth. That's not a column in your data frame. That's how you know it's a latent variable. Okay. It is something that is measured by the overlap between some manifest variables. So a latent variable is indicated by manifest variables, but it does not in and of itself exist in your data frame. Does that make sense so far? Awesome. Okay, so squares and rectangles convey important information. If it's a square or rectangle, it's in your data frame as a column. Oh, good. I'm glad Stephanie talked to you guys about this. If it's a circle or an oval, it doesn't actually exist. Okay. The other thing that we have in our path diagrams are lines. Okay, and there are a lot of different kinds of lines that we can use, but the basics are no line, a one-way arrow. It has an origin and an arrow, but it only has a point on the arrow on one side, or a two-way arrow. And this is one that has points on both sides. Okay. Typically by convention, Casey asked a great question. Let me pause for a moment. Is a residual a latent variable? I want you to answer that, Casey. Tell me what you're thinking. And if you want, you can unmute yourself.
Maybe. It could be a latent variable because technically residuals, you couldn't like look in your data set and find it.
And if the definition of a measured variable is one that you can find in your data set, and a latent variable is one that you cannot find in your data set, an error term must be what?
A latent variable?
It must be a latent variable. Yes, all error terms are latent variables. That is awesome. Great
And
question.
just to chime in real quick here, that is a great question and something everybody should keep in mind, because when we get to the labs and it's asking you like how many latent variables are in this model, you know, in the chat I was talking about it's important to keep track of what's exogenous versus endogenous, because those endogenous variables have an error term, and that is a latent variable. So you, even if you don't see you know, a circle with an E pointing to it, you have to know like, oh, well, this is an endogenous variable, which means it has an error term, which is a latent variable. Therefore, there's X number of latent variables in this diagram. So that's something that you all need to, you know, keep in the back of your mind, because we will be dealing with that once we get to the lab.
Yeah, it's kind of a tricky point. Notice here, I actually wrote down that errors and disturbances, we'll talk in a moment about what a disturbance is, are always latent variables because you don't find them in your data frame. So, okay, coming back to here, I started by saying, this is back a slide. I started by saying that in path analysis was the simplest form of SEM because it only contained manifest variables. That's not actually quite true. There is this error associated with every endogenous variable. So path analysis contains only manifest variables except for error terms, which are latent variables. Okay. So we were talking about the lines that indicate the relations among the variables in your data set. if you don't draw a line between something, you're basically saying, I don't think those two things are associated with each other. One, the value of one depends nothing on the value of the other. When you draw a line with one arrow, you're indicating a direct and directional relation between two variables. Where the variable originated, which we'll call IV, but I don't mean here that it's being manipulated, and then where the variable lands, which we will call the DV. I am purposely not calling this an exogenous variable, and that's because sometimes, I'm going to go backwards in my slides for just a moment to the beginning of class. Sometimes you have these variables in the middle that are both endogenous, they're being explained by other variables, and exogenous in the sense that they are then being used to explain other variables. So these variables in the middle that are both endogenous and exogenous is why it's actually considered endogenous because it has at least one arrow pointing to it. But that's why I don't use the term exogenous when I'm talking here about the origin of a straight arrow. I'm just saying, well, it's a predictor of some other variable. Okay. And then when we have a two-way arrow, we're basically just saying these two things are associated with each other, but there's no directionality of the effect implied. So when I went back here, I'm saying mother and father education are associated with each other, but I don't think it's like mother education drives father education. I just think that, based on theory of similarity and love and whatever, that people tend to find like-minded people or like-educated people. The same is true, for example, with GPA and SRA scores. I'm saying that they are associated with each other, but I'm not saying that the amount of reading achievement you have is driving your GPA score. I could say that, but that's not what this path diagram is telling me. They're just saying, well, we think that they're associated with each other. Maybe it's all reflective of something else, but we don't really care. We just say they're associated with each other. By convention, our two-way arrows, which are basically correlations or covariances, we draw them with a bend. Now, R sometimes will not do that by default. Sometimes by default, it will just show you a straight line. So you do need to pay attention to how the arrows end to see if it has points on both sides or just on one side. But by convention, we draw these covariance arrows with a bend, which is just another visual signal that I'm not predicting that one causes the other. And I use the word cause only conceptually here, not methodologically. When we do path diagrams, we are talking about the directions of things. We're talking about temporal ordering or theory, but lots of times the analyses the data where we run the analyses could not allow us to draw causal conclusions because we didn't actually manipulate anything. Nevertheless, we still think, such as here, that your GPA, SMA, and SRA are causing or driving or leading to a particular educational attainment score in these kids. And we think that because these came at time 1 and this came at time 3, so at least temporally they're proceeding. So sometimes people do call this causal modeling. And Josh is asking if the bend conceptually is basically saying a lack of causality. It's basically silent on the matter of causality. It's basically just saying these are associated, and I'm not theorizing either because of theory or because of the data or because where I'm looking. I'm not trying to understand their specific directional relation. I'm just saying, well, they're associated with each other, but my theory is silent on one kind of driving the other or leading to the other. Okay. Questions so far about lines?
I wanted to chime in with one thing real quick on it before we have to get off here. I just wanted to remind everybody, because I've gotten more than a couple emails asking about the videos and stuff. So I just wanted to remind everybody that, as always, the videos get posted not long after class. They're all posted up on the YouTube channel, UARC Psych Stats. So if you're looking for any of the videos, that's where you can find them.
And I think I put a link to them in our Blackboard page, but I'll double check that now after class and make sure that it's up there. So we'll stop here and we'll keep on talking about path analysis in our next class. In the meantime, I have office hours now, and if you need anything, just drop us a line. Thanks, everybody.